Let's get started learning Kubernetes with a better theoretical understanding.
Okay, let's dive right into this explainer by tackling one of the most notoriously intimidating technologies in modern engineering, which is, of course, Kubernetes. I mean, it can honestly feel like this massive, impenetrable wall of buzzwords when you first encounter it, right? But the real genius here isn't actually that complicated. Once we strip away the heavy jargon, you're going to see a system that's incredibly intuitive. So today, we are going to extract the absolute essentials of exactly how it functions, specifically within Azure.
But before we look at the elegant solution, we've got to fully appreciate the pain of the traditional, fragile single-server model. You know the model that relies entirely on hope. Imagine this scenario. It's 2 a.m. on Black Friday. Your traffic literally quadruples in 10 minutes. In the old days, your monolithic server catches fire, the site crashes hard, and you're scrambling out of bed to reboot things manually. Because relying on one or two massive servers means you're just hoping the hardware doesn't fail. And spoiler alert, it always does. Hope is not a strategy.
So to demystify this system, here is our roadmap. We'll start with the Black Friday nightmare, then move on to decoding the vocabulary, mapping the architecture, and explaining Azure Kubernetes Service. After that, we'll cover workflows for scaling and debugging, and wrap up with the GitOps future.
Let's hit Section 1, the Black Friday nightmare. This right here is the true power of the system. When that Black Friday traffic spikes, Kubernetes quietly clones your application across a fleet of servers so fast you literally sleep right through the event. Instead of manually installing an app directly onto a server, you package your code and its dependencies into a neat, portable container. Kubernetes takes that container and orchestrates it, spinning up, get this, 50 clones in just 3 seconds. It fundamentally shifts us from waking up at 2 a.m. in a reactive panic to a declarative posture where the system just heals itself.
Moving on to Section 2, decoding the Kubernetes vocabulary.
Let's start with the absolute smallest unit. Now, Kubernetes doesn't actually interact with your containers directly. Instead, it orchestrates what we call pods, which bundle your app code and helpers into one manageable unit. Think of a pod as a protective wrapper. Usually it's just one container inside, but sometimes your main app needs a little sidecar helper to, say, pull in secure passwords. The pod groups them together so they share the exact same local network. Basically, they act as the individual cooks on your kitchen floor.
And here's where it gets cool. The absolute core of this system is the reconciliation loop. You declaratively write a deployment recipe on a clipboard, and the system constantly fires or hires pods to make the physical kitchen match your dream state. You don't micromanage the individual pods. You just submit a document saying, hey, I always want exactly 3 cooks running. The manager constantly compares that clipboard to the reality of the kitchen floor. If a pod gets a memory leak and crashes, the manager instantly pulls a brand new one onto the floor to replace it.
But because pods are constantly dying and getting random new IP addresses, we need a service. A service acts like the waitstaff, knowing exactly where to route internal traffic, while an ingress handles the public web traffic. Even if all 3 of your backend pods are destroyed and replaced with totally new addresses in under a minute, the service address remains exactly the same. Internal traffic hits that service, and it seamlessly routes it to whichever pods happen to be healthy at that exact millisecond.
All right, Section 3, mapping the cluster architecture.
Now, I really want you to focus on this architecture diagram we're plotting out here, because it beautifully maps the 2 halves of a cluster, showing how the decision-making brain interacts with the heavy-lifting muscle. On the left, we have the control plane, or the brain. It does 0 application processing, it just makes decisions. It features the API server as the absolute only front door, the etcd distributed database as its resilient long-term memory, the controller manager acting as the nervous system, and the scheduler. Now on the right, the muscle consists of your actual physical or virtual servers. Each worker node runs a kubelet agent that constantly talks back to the API server to report pod health, alongside a container runtime to actually execute your code, and a proxy for network routing.
Which brings us to Section 4, Azure Kubernetes Service Explained. So if you manage raw Kubernetes yourself, you're basically acting as a full-time database admin just to keep that brain alive. It's exhausting, but in AKS, Microsoft completely abstracts the control plane away. They patch it and back it up for free, meaning you only pay for the virtual machines running your actual applications. They are literally giving you the highly available enterprise management layer for 0 cost just to entice you to run your compute workloads on their platform. It's a massive win for operations.
But when you're sizing your muscle in Azure, relying on just 2 massive servers is a total recipe for a 50% outage during maintenance, whereas 10 smaller machines absorb those bumps incredibly smoothly. This is an absolutely crucial architectural decision. Think about it.
If you build your cluster with 2 behemoth virtual machines and just one of them needs a security patch reboot, your pods violently scramble and you instantly lose half your capacity. Scaling out with smaller standard instances provides a vastly more resilient foundation.
Let's look at Section 5, Workflows for Scaling and Debugging. To securely bridge the gap from your laptop to the cloud, you use the Azure CLI Landlord to physically build the apartment building, and then it securely introduces you to the kubectl tenant to deploy code inside the suite. The Landlord tool handles the heavy infrastructure, building the cluster, requesting bigger VMs, but it knows absolutely nothing about your code. Instead, it brokers a cryptographic introduction to the kubectl tenant tool, which securely bypasses the portal and deploys your pods directly.
Now let's trace this on the workflow diagram we have plotted here, because the exact sequence of this architectural workflow cascades entirely autonomously. The moment you deploy your YAML file, these 5 steps build your environment in milliseconds. Step 1, your tenant tool request hits the API server front door. Step 2, it is securely saved into the etcd memory bank as the ultimate source of truth. Step 3, the controller manager nervous system reads the database, realizes reality doesn't match the new truth, and flags an action. Step 4, the scheduler looks at all the available servers and assigns the pod. Step 5, the kubelet agent on that physical muscle executes the actual code. Boom! Done. Of course, things do break. But for immediate fires, Kubernetes gives you incredible visibility. The real game changer here is port forwarding, which acts like a highly secure private walkie-talkie line straight into a pod. You can stream live logs or drop a live shell directly into a container to poke around the file system. But remember, and this is huge, containers are temporary. If you fix something manually in a shell, the moment that pod restarts, your changes vanish entirely. Also, if you have an internal dashboard you need to view locally, you simply port forward an invisible VPN tunnel right to your laptop. Close your terminal, and the tunnel vanishes without a trace.
Now what happens when your physical muscle is totally maxed out? Well, this 2-layered scaling workflow ensures the cluster autoscaler seamlessly orders a brand new server from Azure on the fly. Let's map the timeline. Say traffic spikes at minute 1. The horizontal pod autoscaler tells the manager to hire more cooks. But by minute 2, the physical servers are totally full, leaving your new pod stuck in a pending state. That triggers the cluster autoscaler at minute 3, which reaches out to the Azure landlord, provisions a new virtual machine instantly, and totally averts the crisis.
But we have to talk about the golden rule for day 2 operations, setting CPU and memory limits. Why? Because a greedy pod with a memory leak will cause the brain to assume the node died and violently evict everything. If a tiny internal app consumes all available memory on a server, it starves that kubelet agent we talked about. The agent stops reporting to the control plane, the brain assumes the server is dead, and it disrupts every healthy app on that machine. You have to explicitly define resource boundaries to force the system to restart the greedy pod before it takes down the whole ship.
Finally, Section 6, the GitOps infrastructure future.
GitOps forces you to stop acting like a mechanic manually turning wrenches and start acting like an architect whose blueprints are autonomously built by an agent. Let's be honest, human beings typing terminal commands is inherently error-prone. With GitOps, you actually never touch the cluster manually. You write your desired state, commit it to a Git repository, and a software agent living inside your cluster constantly watches for changes. The moment you approve the code, the agent pulls the configuration, and the architecture silently and perfectly builds itself.
It's a profound paradigm shift for sure. And I want to leave you with this provocative thought about a future where servers become virtually invisible. If an entire global, self-healing data center architecture springs into existence automatically just from committing a text file, are we approaching a point where the very concept of a physical server fades away entirely? Think about it. We are moving from managing machines to managing intentions. So fire up the portal, configure some boundaries for your pods, and go build something highly available. Keep learning, and we'll catch you next time on The Explainer.